No, like thermodynamics is pretty different. If you are not aware with the terms that we have used so far, you will still able to understand it if you are revising regularly. So it is not connected much with the previous four chapters. It is an entirely new, I would say, branch of chemistry because
Yeah,
here we are going to talk in terms of the energy exchange, right? So let us talk about it. Thermodynamics, right?
yeah.
So the general principle of chemical thermodynamics is what? The study of flow of heat or any other form of energy into or out of a system as it undergo a physical or chemical transformation. It is called thermodynamics.
Thermodynamics.
So in simple words, what we can say, whenever you are exchanging energy, right, into or out of the system, then you will consider that entire process as a thermodynamic process. Is it not?
Yeah, yeah,
So what is the objective of thermodynamics? The objective of thermodynamics is to improve the efficiency of the process of transformation between energy and work. You are trying to make your system or anything, like suppose you are making an engine, right? So you will try to make that engine as much as efficient as possible, right? So all of that thing that you are going to do with your engine, that will be considered you are doing some thermodynamics with it or not.
yeah.
So basically between work and
Conversion.
energy, conversion between work and energy is thermodynamics. If you are converting work to energy or energy to work, you will talk about it in thermodynamics. So let us see. Suppose you had energy one and you converted it into some other energy, and again you convert it into the initial energy. You are just exchanging energy. So this is a thermodynamic process. So can you tell me like uh what is work basically? You
What
must have
is
heard
work?
work
Yeah.
done. What is work done?
Um, yeah. Amount of work is applied on an object. Like amount of work that is applied to move an object. That is work done.
Okay, so in simple terms, if you have to say it in a very short like way, you can say work done is basically force into displacement, right? You are applying force and the
That's
thing that you
formula.
are that's the formula, the simplest thing, right? You can say so the work
Yeah.
done that we are talking about is basically energy. The energy, you can take any form of energy, it is basically work done and vice versa. So if you are converting work into energy or energy into work, you are basically exchanging the energies. Suppose you are converting kinetic energy into potential or potential into kinetic again. So it is basically will be talked in thermodynamics, right? Are you getting what I'm trying to say?
Yeah.
Whatever work done you are thinking about, it is a form of energy. So what are the scopes of thermodynamics? What thermodynamics is going to help us understand, right? Why we are studying it. And we have to study it in chemistry as well as physics. So it must be important, right?
Oh,
So you will be studying this in physics as well. So you should brace yourself because I think the physics thermodynamics is a bit
that's
more.
why I saw thermodynamics in physics textbook.
Mm. So predicting the feasibility of reaction. What do we mean by this? What does this feasibility terms means? Feasibility means the probability of something, like if something will happen or not. The probability of that is called feasibility. So, if
Okay.
you know the thermodynamics, you can tell whether the reaction is going to proceed or not. Whether in chemical reaction, what you are doing, you are basically cooking. Like we do in the kitchen, we are mixing milk plus sugar and then tea
Yeah.
leaves to make tea. In chemistry, we are mixing different chemicals to make something, right? So thermodynamics will tell us whether the thing that we are hoping to get, will we get it or not? What are the chances of that thing to be prepared, right? So the feasibility of reaction will be predicted by the help of thermodynamics, right? Suppose you are
Mm.
making tea in the kitchen, whether you will be able to make tea or not, what will tell you about it? Thermodynamics.
Oh, okay, okay, okay.
The second
What's
point,
RX?
Rx means basically reaction. I write a reaction in short like this. Rx. Right?
Oh,
What next? Calculate the energy changes if the reaction does take place. Suppose your reaction is happening, right? It is taking, let us say, suppose 1 hour, right? We don't know. It might take
uh-huh.
a day. It might take a minute. We have no idea. In thermodynamics, don't talk about the kinetics. How much time it is taking, thermodynamics will not talk about it. What does thermodynamic will talk about? The change in energy. Thermodynamic will tell you what amount of change in energy you are observing while you are performing that reaction, right?
What amount of change?
Yeah, change in energy. Suppose it is exothermic reaction, it is giving you some 500 kilojoule of energy, right? Or it is an endothermic reaction, you have to supply
Yeah.
500 kilojoule energy. So what will tell about you? Like whether it is what energy exchange is happening, it is thermodynamics, right?
Okay.
The next one is calculate the extent at which chemical reaction process. How much reaction will proceed? Suppose you are making a compound and you are getting only 80% yield. You know what yield means?
Yeah. Yeah. I think I know what yield means.
Yeah. So suppose you are hoping to get 100%, 99% pure compound, right? But you are
Huh.
getting 64% or 70%. So till what extent your reaction will proceed will be talked in thermodynamics, right? We will go into them one by one. So this is the general idea of thermodynamics. Like how does it help us to understand a chemical reaction? In physics, you will be talking about Carnot engine, right? You will be talking about some refrigerator thing, I guess. I studied it while I
In
was in VC, right?
I think
So those topics will be added. So what are the limitations of thermodynamics? It is applicable to macroscopic system, not to the microscopic one. To apply thermodynamics on microscopic system, you have to take help of statistical thermodynamics. The thing that I showed you just a few minutes ago, before, right? Statistical thermodynamics. To deal with microscopic particles thermodynamic phenomena, you have to use statistical thermodynamics. But you are lucky enough, you don't
okay.
have to even think about it. So, what is the first limitation of thermodynamics?
They are only applicable for microscopic
Macro.
at
Not on
micro or
microscope.
macro.
Macro, it is written, you can read it.
Oh, okay, okay. Macroscopic systems, not in microscopic.
And the second point is can't predict speed of the reaction or time taken to reach equilibrium. Thermodynamics do not talk about, or you can say thermodynamics does not talk about the speed of the reaction. It won't give you an idea about how long it will take your reaction to complete. It might take a day, it might take a month, it might take a week, it might take a minute. Thermodynamics has no concern about it. Thermodynamics only talks about the exchange of energy, right?
Yeah,
To understand the kinetics, the speed, we have an entirely different chapter that you are going to deal in your 12th class. The name of the chapter is chemical kinetics, right?
yeah.
So these are some two limitations. So what else? Let us talk about it. Suppose you have a system E, right? Or suppose you have some water and you are giving
Mhm.
100 joule of heat to the entire water container, right? What we
Okay,
are doing? We have some E, we are giving it 100 joule energy in form of heat. And now we have E plus 100 joule of energy. Here we can say 100 joule energy provided to the water in beaker, but we can't tell how much energy will individual water molecule will observe. You are supplying 100 joule of energy to the whole water beaker, but can you tell how much energy does a individual water molecule will observe? Because in a beaker of water, there will be billions of water molecules. So can you
yeah,
predict like how much a single water molecule is going to absorb from this 100 joule of energy? It would be very complicated.
yeah,
So thermodynamics also does not talk about microscopic. It is only talking about macroscopic. It is talking about the beaker. This is the example for your first limitation, the one applicable on
Why
microscope, right?
beaker? Because water has like hundreds of thousands of water molecules, so it would be hard. So they're using beaker.
Yeah, they are just talking in terms of beaker at macroscopic level. They are just saying we have a glass of water. I am giving 100 joule of energy. That's it.
Mm.
I am considering it a macroscopic entity. But if I go into the microscopic level, if I talk in terms of individual molecules, it would be very complicated for me. And simple thermodynamics cannot explain the processes that are happening at microscopic level. This is just an
Yeah, only
example,
macro.
only macro, right?
So how, what do they do with
Uh,
beaker?
we, they will just simply heat it. You must have a beaker in your lab, right? Have you attended any
Yeah,
lab in school? So
yeah.
they are just heating that beaker, and inside the beaker we have water. We can say that this entire water, like the entire water that is present inside beaker, it is absorbing 100 joule of energy. But we cannot say how much energy an individual water molecule is absorbing. Oh, sorry, absorbing, right?
Only the glass. Yeah.
Only the macroscopic level. We can consider it as
Yeah.
a big system. So
Okay.
the second limitation, let us take an example for that as well. Suppose you are reacting A plus B in hope of getting something C, right? Thermodynamics can tell A plus B will give you C, but it cannot tell the speed of the reaction, or you can say how long it will take. Suppose you are mixing A plus B, thermodynamics will tell you that you are going to get C, but thermodynamics will not tell you how much it is going to take, like how much time it is going to take you to reach C, right?
It doesn't tell the time it takes to reach the sea, but it gives you C.
It will tell you that you are going to get, which is C, but it will not tell you how long it is going to take. What is the speed of the reaction, right?
Okay, okay.
Is it making sense?
Yeah. But how would we know how long it will take?
I told
Well,
you
we
now,
should also know that it will take
we
this
know
much time.
everything. We know everything, but that is an entirely
So
different
humble.
field of chemistry. It is an entirely, see, thermodynamics, we will use it to study energy exchange. Then to
Okay.
understand the speed of reaction, we have an entirely different, you can say, topic. That is chemical kinetics. With the help of chemical kinetics, we can tell how long a reaction is going to take. Uh,
Oh, okay, 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 okay.
right.
It's
So
another branch.
yeah, we have specialization. Like we have special persons. Like we have a swimmer who is good at swimming. We have a climber who is good at climbing, but they cannot do all the
Oh,
job alone, right? We have to take the help of both to perform specific tasks.
yeah, I understand, understand, understand.
An example, you are trying to make water. Thermo says it is possible. Thermodynamics says if you are reacting H2 with O2, you will get water. Right?
Yeah.
But how long it will take, it cannot comment on that.
Sorry?
How long it is going to take to get that
Oh,
water
okay.
molecule, it is not able to tell you that. Right?
See.
So in thermodynamics, there are some frequently used terms that we should know. It is system, boundary, and surrounding. Right. Whenever you are studying thermodynamics, you have to face these three terms, and they are pretty simple. So, what is a system? It is written over here. Can you explain me after reading it? Try to see what is a system.
What is that word?
Which one?
For court.
Yeah, in this one
Mm,
or
yeah, it's the first line. A system is that for court.
the part is part of the universe.
Okay, part of the universe um with is under thermodynamics study and The rest of the universe is surrounding. What does it say?
Give me a second. See, a system is that part of the universe which is under thermodynamic study, and the rest of the universe is surrounding. Suppose you are studying a system, or you are studying anything. Suppose I am, do you have a water bottle or anything? Suppose, uh, in which device you are taking this class?
Laptop.
Laptop, right? So if you are seeing your laptop becomes system,
Yeah.
right? And everything apart from it will be considered as surrounding.
Okay.
And the thing that is separating your system with surrounding is called boundary,
Oh.
right? So let us take some chemistry example. Let me read it out, the second one. The real or imaginary surface separating the system from surrounding is called the boundary. So if you see this, suppose you have a system which I have drawn with your yellow color, right? This is your system. And
Uh-huh.
what would be the surrounding? Surrounding would be everything which is outside it.
Let's take a water bottle as a example.
Hmm. Let me just a second. Suppose you are talking about water bottle, right?
Mm-hmm.
Suppose your water is your system, okay?
Mm-hmm.
And everything apart from your water is your surrounding.
Mm-hmm.
And your bottle, the outer line, the plastic thing, which is separating
Mm-hmm.
water from surrounding is called boundary.
Okay, okay, now I understand.
Right? So we have basically homogeneous and heterogeneous systems. When a system is too outly uniform, it is homosystem. Homosystem is made of one phase only. Suppose, I hope you know, I must have told you what are homogeneous mixtures and what are heterogeneous mixture, right?
Yeah,
So homogeneous mixtures are those which are uniform throughout. You cannot differentiate
yeah.
between them. They will appear as a single entity. So if you are talking about homogeneous system, then those are the systems where it would appear as they consist only one phase, right? Suppose you are
One
seeing
pace.
one phase.
Okay.
Suppose you are seeing a mixture of gases, right?
Uh-huh.
And the mixture of gases, both the gases are colorless. Would you be
Okay.
able to differentiate between, like, would you be able to say this is your system or this is your surrounding? They would appear as a one,
No.
right? So it
Yeah.
is an example of homogeneous system. And the other one is two solutions. What are two solutions? Again, homogeneous solutions where you are not able to differentiate between the phases, right?
What are those phases?
Suppose you are mixing salt in water. After the salt is completely dissolved, would you be able to see the salt molecules?
No.
Salt as journal? No, no. So that's a homogeneous system where you are not able to
Okay.
differentiate between phases. But if you are
Yeah.
doing the same thing, but you are putting sand into your water bottle, so you are able to see
That's
sand.
heterogeneous. That I understood.
Mhm. The same concept is applied here, but in thermodynamics. So the thing is, we are going to study the heterogeneous systems. The homogeneous system does not make any sense, or they are not able to help us to solve real problems, to be honest. Because a
Oh,
mixture of gas, how would you able to convert it into something applicable? A heterogeneous system is one that consists two or more phases. Simple as that, right?
yeah.
So let us move ahead. So types of thermodynamic systems. We have open system, we have closed system, and we have isolated system. So what are open system? Open system is a system where you are allowing matter as well as energy exchange. For example, mm, chai. I hope you drink chai, or are you a coffee person?
Yeah, I drink those, but I stopped. Yeah, I know what those are.
Okay, so when you are drinking tea or chai
Mm-hmm.
and
Mm-hmm.
your cup, like your you haven't covered your cup with anything. So what you will
Yeah.
observe? You will observe, like, first of all, energy will be transferred. Your tea will become cold.
Yeah,
That is the escaping.
energy is escaping.
Energy exchange is possible, right? Also, what you
Yeah,
observe, there are some what I can say, like the water is escaping. You see now the
yeah,
fumes. So matter is also exchanging.
yeah.
So this is an example of open system,
Okay.
right? So
Yeah,
what is a closed system? A closed system is something, again, you have your cup of tea, but you covered it with your something, a lid, a plate, anything. You have just covered it.
yeah.
So now your tea is going to get cold or not.
I mean, it still gets cold.
So the energy is still exchanging. The energy is still escaping. The, like you can say,
It's
ener-
exchanging.
exchanging. But will the matter
But
escape or
the
not?
matter doesn't escape.
So it is an example of closed
A
system,
closed system.
right? So closed system is one that cannot transfer matter but can transfer energy into in the form of heat, work, or radiation and form its surrounding to and from its surrounding. Right, let me give me this one. Radiation to and from its surrounding. Example would
Radiation.
be
Where did
mobile.
radiation come? Oh, okay, okay.
Energy is basically radiation, right?
Yeah,
So example is your mobile phone, your laptop, or your tea, but you just cover it with something. Cup of
yeah.
tea, you covered something. So can you tell me why have I written mobile and laptop as an example of closed system?
There is no matter escaping because there is no matter inside mobile and laptop
Okay, so
unless.
you are able to understand it, right? Why I have put mobile and laptops for the case of.
No.
Okay, so let us talk about it. Suppose you are using a mobile phone. You will
Okay.
suppose you are using it for a prolonged period of time. What would you observe? Your phone might heat up,
Yeah,
so energy is getting exchanged.
yeah.
But are you seeing any matter getting exchanged? Your
No.
mobile phone as a whole still remain intact. So it is an example of closed system.
Okay.
So the last one is isolated system. So if you see the trend, the first one was allowing matter as well as energy to like the exchange of matter and energy. The second one
Mhm.
put a restriction over matter. The third one will put the restriction over matter as well as your energy. So the isolated systems are those where energy as well as matter are not allowed to exchange to and from the system to surrounding, right? Is it making sense?
Yeah.
So an isolated system is one that can transfer neither matter nor energy to and from its surrounding. So the best
Okay.
example for it is universe, right? Your
Yeah.
universe is neither exchanging matter or energy because if universe is supposed to exchange these two things, then there should be something beyond the universe, right?
Yeah.
So universe is an example of closed system. What else? Like this is not the most appropriate example, but you can consider itself. Boiling water in thermoflask. What are thermoflasks? Thermoflasks are supposed to keep our like
I know
water.
what thermoflask is.
So what's its purpose?
To keep a liquid in a same temperature.
Right. So it is again somehow we can consider it into isolated system because it is restricting.
But how though? How? What is the difference between isolated system and closed system?
Isolated system is allowing your energy to exchange, but your
Yeah.
isolated won't.
Okay, that I understood. What about other like what makes the energy not to change in isolated system, but it changes in closed system?
See, if you see the thermoflask, right? Thermoflask
Mm-hmm.
is made with a specific substance, or you can say metal, which restricts the exchange of energy. That is the whole reason why if something is hot inside that bottle will remain hot for a longer period of time. So it is resisting the exchange of energy, and matter will
So
not exchange because
metals,
no. See, the metal is responsible for that, but the as a whole, it is an isolated system. The reason being because matter as well as energy both are not getting exchanged, right? The best example for this is universe. Suppose if universe is supposed to exchange energy or even matter, it needs something beyond it, right?
yeah,
So, like till now, are we able to uh like develop any theory, like we have developed those theories, but are we able to prove that there is something beyond our universe? No, we haven't been able to prove that, right? So
yeah,
if the universe is the only thing, the entire thing, so everything is inside universe, so will the universe be able to exchange something? No.
no,
So it is an example of isolated system. Is it making sense?
yeah,
Okay, so I will ask you a question then.
okay.
Hmm. So you have a cup of tea and it
Mm-hmm.
is just lying there. You haven't covered it with anything, so
Mm-hmm.
it is a which sort of system?
Open system,
And if you have covered it with the lid, then
closed system,
now you have transferred your tea into thermoflask. Then it is
then isolated system.
so. So you know you are smart. You are able to answer it. So you must have understand it now.
Yeah,
Okay. So we used something called boundary, right?
yeah.
What is boundary? Boundary is the thing which is
The
separating our
thing that separates the system and the surrounding.
good. So let us talk a bit more about this boundary. We have two sort of boundaries. One is adiabatic and one is diathermal boundary. So what are adiabatic boundary? It is basically a boundary which is restricting the exchange of matter as well as energy, right? But what are diathermal boundaries? These are allowing energy to exchange, but they won't allow matter to exchange. So do you know now what sort of boundaries do we have?
I think
So if I just connect this or use this with the previous cases, suppose if I am talking about thermoflask, which type of boundary are we considering there? Adiabatic or diathermal?
arithmetic,
Good. But if I'm talking about isolated, then what?
diathermal.
So is it clear now?
Yeah, but the names are hard to memorize.
You don't have to memorize them. You will be familiarized with them as we move ahead because you are going to use it in this entire chapter, right? So
Okay.
you will be familiarized with them. Now, we have another type of boundary, which is movable boundary, right? Simple, you can say. A piston. I will explain what a piston is. Piston is
I know
a
what
sort of
piston is.
piston can move, right? You can move
Yeah,
the piston, so it is again
yeah,
a form of boundary. Now, now, macroscopic properties. So macroscopic properties, as the name suggests, they are the properties associated with something which is macroscopic, right? Suppose your bottle,
yeah,
your phone, the properties associated with these type of things will be called macroscopic properties. So let us talk about them. Properties associated with macroscopic system consisting large number of particles are called macroscopic properties. For example, pressure, volume, density, temperature, composition, surface tension, etc. These are the examples of your macroscopic properties. And what are
yeah,
macroscopic properties? What are macroscopic systems? These are the systems which are consisting of large number of particles.
yeah.
So let we connect it and related with state of matter. When macroscopic properties of system have definite value, the system is said to be in definite state. Whenever there is a change in any of the macroscopic property, the system is said to be in different state. So this might be sounding a bit confusing, but it is very simple. You just need to think about it. What it is saying, when a macroscopic property of a system have definite value, right?
Mm-hmm.
Suppose your
What does
system has,
definite value mean? Like same value?
yeah. Suppose you are talking about a macroscopic property, for example, volume, right?
Mm-hmm.
Your volume of the system is 10 liter.
Yeah.
So the system is said to be in definite state. So your system has a
Yeah.
definite state. But whenever there is a change in any one of macroscopic property, suppose you are changing the volume from 10 to 8. So you will say your system is now in an entirely different state or not.
Mm.
So
Yeah.
whenever you are changing a macroscopic property, let it be pressure, volume, temperature, whenever you are causing this change, then you will say your system is converting into a new thing, different state. Suppose
Yeah.
initially you had system A, you convert it into B. So what you will say? In system A, your pressure might be P1, volume would be P1, temperature T1, and number of moles will be N1. But as you are changing its states, then the pressure, volume, temperature, number of moles, etc. will also change. So there we will say the state has been changed. On what the state change will depend on the macroscopic properties. Is it making sense?
Yeah. But I guess, yeah, sure.
You can ask questions. You don't have to think like,
This is like a hypothetical thing, right?
no, this is not
Um,
hypothetical.
because
We can.
in macro
Mhm,
in
mhm.
macro system, a macroscopic system, it is not easy to change the you know I mean like properties, change the properties.
It is very
It's
easy
gonna
to.
be the same.
No, no, no. In macroscopic, it is very easy to change the properties. Suppose. Shall we take tea again, or do
Okay.
you want water? Your choice.
Let's do take TTT.
Tea. Okay. You have a beaker, and
Mm-hmm.
you have transferred some tea into it, and the volume
Okay.
you measured in a conical flask, and the volume was suppose 100 ml.
Okay.
Right? Now this is a specific state of a matter. Your this beaker has a specific volume, specific temperature, specific pressure, and specific number of molecules. Or not?
Yeah.
Now, if you are heating it, suppose you are heating it, so your temperature is changing.
Yeah.
Your volume will also change or not because some of the tea might get evaporated.
Yeah, the tea volume will change, not the container. But
So
yeah.
I'm talking. And your pressure will also change because if you are applying heat, the pressure is also going to change.
Yeah.
And if the water, like the tea is escaping due to the evaporation, then the number of molecules will also change.
Yeah,
So
that's
after,
correct.
so after heating it for some time, you can say, na, like now my state is different. Now it is converted into a new state. What was the reason, or what was the like things that made sure, or you can say give you the reason or explanation of this change
You
of
said
state?
macroscopic, right? You're saying
Yeah.
microscopic things.
I'm not talking in terms of microscopic. A volume is not a microscopic property. See, 100 volume, you
Um,
can see 100 volume, 100 uh, liter, oh sorry, 100 milliliter. You can see it with your naked eyes, right?
so you're taking actual tea. Okay.
Ah,
I
whatever you will get in a
I
tea.
thought that you're talking about the container or something.
No, we are talking about the system. Are you not able to see this? Uh, or this bluish? I showed it like this.
Yeah.
This is the actual thing.
Okay, fine. Yeah, understood.
And whatever you are able to see with your eyes is a macroscopic thing, right? So if you are
Yeah.
observing a change in that, you will say your state has changed.
Okay.
And what is responsible for the state change? Those are macroscopic properties.
Okay.
So these are also called state variable or parameter. We are going to use this term, so you should be aware of it. And these macroscopic properties define the state of a system, right?
Yeah.
Is it clear or you have
Yes,
doubts?
yes, yes, yes. It's clear. It's clear.
Now, equilibrium, right? The name of the next chapter is equilibrium. We are going to talk in very detail about what is equilibrium basically. But for now, let us use equilibrium for thermodynamics only, right? We won't go into depth. We will just understand equilibrium so that it can help to understand us thermodynamics. Equilibrium, right? An isolated system is in equilibrium when its macroscopic properties remains constant with time. Can you explain this with an example? Like the way I took, right? Can you give me an example? Can you think about it? What are we talking about if I am saying like if we are saying like our system is in equilibrium?
Um, just a
You might
minute.
think about it.
What about thermoflask
Thermoflask, okay.
with
So
tea?
you are saying if I'm using thermoflask, I can say my system is in equilibrium.
Yeah.
Why though?
Because it's an isolated system.
Okay, but how are you relating it with equilibrium? What is equilibrium and how you are connecting it with your thermoflask?
Um,
You are on the
I
right
don't know.
track. You just have to connect it.
Okay. Just a minute. Just a minute. Just a minute. Because okay. Um, because it is always constant. The energy and the molecules are always constant. It won't change, is it? Does it?
With time, it will stay constant, and that is the entire thing about equilibrium, right? The macroscopic
Yeah.
properties should remain constant. Good. So let us talk about thermodynamic equilibrium. Am I missing something? Yes. Okay. Thermodynamic equilibrium. Am I missing a page? Mm, uh, Just give me a second. I think there is some. Check it. Mm. Yeah, I missed a page there. So I will add this while I'll be sharing the PDF now. So let us talk about it here. As you mentioned yourself, what is equilibrium? So we are going to talk about thermodynamic equilibrium. So basically, we have three types of thermodynamic equilibrium. First is thermal equilibrium. Second is mechanical equilibrium. Third one is chemical equilibrium. So let us talk about them one by one. Right?
Yes.
Am I audible? So what is a thermal equilibrium? Thermal equilibrium is when no further heat exchange will observe. If the heat exchange is not there, you will call that thermal equilibrium. It is a part of thermodynamic equilibrium, right? What if
Yeah.
we are talking about mechanical equilibrium? In mechanical
Say the
equilibrium,
thermal again. Say the thermal again.
no further heat exchange. You won't observe any heat exchange.
Yeah, that was clear last time. Yes.
Now mechanical equilibrium.
Okay.
Suppose you are uh, putting some pressure from piston and it is going like this. Are you seeing
Okay.
these figures? The external pressure you are applying and now your piston is here. Suppose there were
Yeah.
gas inside this, gas molecule will compress, intermolecular repulsion will increase. So at the moment where your external pressure is equal to internal pressure, you will call this point mechanical equilibrium. When system achieve, oh sorry, this is about mechanical equilibrium. When your external pressure that you are applying on piston will become equal to the internal pressure due to the gases. Suppose this is gas here, right?
Yeah.
And if you are putting the pressure from the piston, the gas molecule will come closer to each other. As they
Yeah.
are moving closer to each other, there will be the repulsion,
Yes.
and due to that repulsion, they will uh, apply the pressure in the opposite direction to like what you can say, stop the external pressure. So at the point where your external pressure is equal to internal pressure, you will call that mechanical equilibrium. That your system is now at equilibrium mechanically.
Um, can you relate this with an example of a syringe?
A syringe. Okay, suppose um, it's a okay. Let me think.
Closed end syringe.
Your syringe and it's closed. Suppose you are, we can do that. You have placed some sort of liquid inside your syringe, right? And you are
Uh-huh.
pushing it like this. What you will observe,
Yeah.
the air, when you are pushing, the air will be pushed. But at
Yeah.
some time, you won't be able to push it further because you have reached
Yeah,
a
it will
point.
be
Huh,
where it's hard.
So at that point, you will say you have achieved mechanical equilibrium because now the pressure that you are exerting from the outside is equal to the pressure that your molecules inside the
Oh, okay,
syringe
okay, okay,
is
okay.
applying, right?
Yeah, I understand.
The last one is chemical equilibrium. Chemical equilibrium is again pretty self-explanatory as with for the case of thermal equilibrium. Here, no exchange of moles, right? At chemical equilibrium, you won't observe any exchange of moles, right? If
Yep.
initially you had 10 moles, at the final stage you will also have 10 moles.
Yeah.
So when these three equilibriums are present in a system, when system achieves all the above three equilibriums, then the system is in thermodynamic equilibrium. To attain a thermodynamic equilibrium, your system have to follow all these three equilibrium state, or you can say your system has to achieve all these three equilibrium state. Is this making sense? Or now is it becoming boring?
Kind of. The mole one?
Uh, The mole one is no exchange of moles at equilibrium.
No exchange of moles. How is that possible?
Again, let us take some tea. You are heating
Okay.
your tea, and after some time, your like the tea will evaporate. The initial moles will be like initially you might have 10 moles. After evaporating, you will have 8 moles or
Oh,
not.
okay, like that. Yeah. But if we use a closed system, it won't escape. So it's a
Yeah,
mole
equilibrium.
equilibrium.
Yeah, chemical equilibrium,
Okay. Yeah, now I understand.
right? So this was about. I will add this slide in your PDF.
Yeah, sure.
And one more thing. Last year I taught thermodynamics a little bit in much detail, right? And that was not
Yeah.
really needed. So this time I will only teach the thing that are in your syllabus or that is going to come in your exam. Because last time I was studying thermodynamics and statistical thermodynamics, so I was a bit more like unusually enthusiastic about that. So my students
Okay.
has to face the consequences of that. So they are literally scared of thermodynamics and
Suffering.
are suffering. So I don't want you to feel that way. So I will teach you only the stuff that is needed.
Okay.
So the PDF that I'm going to share you after this class, that is pretty scary. I will share you a new PDF after some modification of the previous one. So the last PDF that you will get is the one that you need to actually study. The rest is just the scary PDF that you don't have to worry about.
Okay.
So shall we go back to our previous PDF? I think we gotta go back. These two pages are. Okay, so extensive and intensive properties. This is again important concept. They might ask you directly, what is extensive or what is intensive properties. So have you ever heard about these two terms?
No.
Right. So let us talk about them. Extensive properties are the properties of the system that do not depend on the bulk of the system or amount of the system. And in the bracket, I have written additive. So they are additive as well. So what are extensive properties that do not depend on the bulk of the system or amount of the system and also are additive? So let us talk
What's
about
bulk and
intensive.
what's additive?
It will make sense. Just give me a second. Let me tell you the definition of both of these. Then I will take some specific examples. Right. So
Okay.
intensive property are the property of the system that do not depend or is independent to the amount of substance or bulk of the system present in the system. These are non-negative. So let us take some specific examples to understand it better, right? So, okay. Hmm, I think I have written it opposite. So let us start. The extensive property examples are resistance, mass, volume, energy, entropy, and the other thing that I have mentioned, etc., etc. So let me take an example. Okay. Suppose we are talking about resistance. What
Okay.
is resistance?
Resisting something.
Have you heard about Ohm's law?
Yeah.
What is Ohm's law?
Resisting the current.
V is equal to IR, I guess.
Yeah.
So if I'm talking about R, I can say V by I. And also
Yeah.
resistance is proportional to your length of the wire and area of the wire, right?
Yeah.
So resistance is an extensive property. Let us justify it. Suppose if you have a small wire, will the resistance will be more or less?
If we have a small wire. How small? Like lengthwise or area-wise?
Suppose you have a wire, the length is so like your finger, right? And you
Mm.
have a wire, the length of your hand, entire hand. Which one will have more resistance?
Okay. The more resistance is the hand one.
So is it depending on the amount of the substance and bulk of the substance? Like if you have
Yeah.
more amount, then the resistance is more, and if you have less amount, the resistance is less. So it is an extensive property, right? because it is depending
Yeah.
on the amount and whether it is additive or not. Suppose you have this much amount of length of wire and you have just added your finger one as well. So they are additive. You can connect wires or not.
Yeah.
So it is additive as well. So it is an example of extensive property. Let us take some more. Uh, suppose you are talking about mass, right? So whether mass is an
Okay.
extensive property or not, can you justify it?
Mass.
Hmm.
Um, I don't know. It's kind
See,
of cloudy.
you have to go back to the definition. Just give me a second. Let me know those. So just read this definition again
Okay.
and then think about it, whether mass is an extensive property or not. You have to relate the resistance and wire example while you are thinking.
Okay. Okay. Okay.
So tell me,
Intensive and extensive are both opposites.
uh,
Um,
by the definition, they have opposite meaning, but you have to
yeah.
understand it. You don't have to just uh, uh, rote memorize it. I told you something about ratta. You don't know, na? What is the meaning of it?
Which one?
The ratta word that I used yesterday or the last class, I think.
Um, I think yeah.
You just don't have to rote memorize it. You have to understand everything because if you go by that method, then there are a lot of things and you can't just rote memorize
Yeah,
them.
I'm not memorizing it.
So tell me, what are you thinking if you are reading the definition? How mass could be extensive? Suppose,
Extensive.
suppose
Because it depends on bulk due to that due to what is that in a pressure it doesn't push down mechanical
you
something,
don't
yeah.
have to go there. You don't have to go there. Just keep it simple. Suppose you went
It
to a
just
shop.
depends on bulk. It just
Bulk.
depends on bulk, yeah.
10 kg is different, 20 kg is different, and you can add them as
Yeah.
well. Suppose you are buying 10 kg sugar and your
Hmm.
friend is buying 20 kg sugar. Both are different because the amount is different, right? You will, it might take you 15 minutes to eat 10 kg sugar, and it might take you the double time to eat the next one. Or if you are using them for some specific task, they will have like different time limit, and you can add
Yeah, I
them as
understand,
well.
I understand.
So what should be the case if you are talking about intensive property? The examples are given, and I'm going